All right, so in this tutorial we're going to review what we discussed in class as the components of any electrical circuit. So big picture, there are three main components. Each serves a role. They must all come together in order to deliver energy. Okay, so keep in mind that the whole point of electrical circuit is to transfer energy from one place to another. Okay, and so we do this using electric fields to circulate charges. So charges are like our little trucks that are carrying the energy from one place to another, and we go from high to low electric potential. All right, you guys know potential, electric potential as voltage. Okay, so any voltage source has a positive and negative side. One is at high potential, the other is at low potential, and things fall down from there and deliver energy. Okay, so our three components. We said before we need a voltage source, okay, and that maintains a constant maintains a constant electric field. Okay, that's like our push on the charges, and it's also our input of energy for the system. So again, that's your battery. That could be a generator, a solar cell, a capacitor. I'm trying to think if I'm missing something there, or a static generator. So we have the potential. An outlet in your home, you got potential there. Now we want to tap into it. But to deliver the energy from that potential, we need conducting paths. Okay, there's two reasons you need conducting paths, and those are usually your wires. They don't have to be wires, anything that's conductive, but generally that's the case. So the conducting paths do two things. They provide a, if you will, roadway for the charges to move, and more importantly, they are the source of the charges. Okay, so we do not create charge from nowhere. The charges are not in the battery. They are everywhere in the circuit. Okay, they are the electrons that are part of metals that are free to move around. You just got to push them around, and that's what the voltage source does. So what's the whole point of this? Well, if we're pushing energy by the charges around, we have to deliver it to somewhere. I'm sorry. And so the third thing that we want is what we call load. Okay. So a load is like your light bulb, or another word you might use, an appliance. Okay, so in your home, that's a toaster, a refrigerator, a speaker, a computer, a television, etc. What you're doing with the load is you are converting the electrical energy from your voltage source into other forms. So that could be heat, that's easy to do. That's with a toaster. You get motion. If you have a motor, that's harder to do. You can get light. That's easy or hard depending on what you're trying to achieve, and sound, etc., etc. Okay, so those are the three things, and now what we want to do is represent them, how they appear in a circuit schematically. Let me go back to this note. All circuits are electrically neutral, so that's important. There's no buildup of charge anywhere. Okay, it's just taking the existing electrons and pushing them around. All right, so in the video we saw before, that we took the components and reduced them to a schematic. And the schematic is in your reference tables. They're very simple, so you don't have to remember them all. So let's start on voltage source. So voltage source represented with two parallel lines, where one line is longer than the other. So the longer line is always the positive side, and the shorter line is the negative side. This is a cell technically, and if we want a battery, we just put a bunch of them together. So sometimes you see multiple sets of these parallel lines, which just represents a bunch of cells. A resistor, the load are these black lines here, and they're not drawn with curves, they're drawn as rectangles or combinations. All right, a resistor or the load, okay, the symbol for that is a squiggle line that looks something like that. Oops, I misaligned it. And then if it's a light bulb, which is a particular type of load, we usually give it a circle, maybe with an X through it, or maybe sometimes with a filament through it. Okay, so again, we have battery, load, or another load, and the wires. And if there's a switch, that's pretty straightforward. So I just want to finish with possible circuits and whether they would allow energy to flow or not. Okay, so I want you to try these and then we'll answer them. So I'll do the first one with you, and we'll go from here. So let's say I have a circuit that looks like this. All right, so first question we have, do we have a complete loop? And this question answer is yes. We're starting and finishing. There's no open or no breaks in the loop. Is there a voltage source? Yep. Are there loads? Yep. And do our wires lead from the positive and negative? And the answer is yes. So this one is fine. What's different from what we introduced in class is that there are two loads here. There's no rule that says you can't have more than one load in a circuit. In fact, these are connected in such a way there's only one path through them to get from the positive to the negative. So this is called, and we'll talk more about this later on, a series circuit. All right, and those are a little bit more complicated than the simple circuit, but it's not too bad. All right, in this one we have a loop, we have resistors, we have wires, but there's no voltage source, so nothing's going to happen here. Okay, so that's a no-go. In this one, what's different about this than the first one? We have two voltage sources, two batteries if you will. We have a set of wires and we have a load, and they're connected in a loop. So everything looks good, except that if you look closely at the orientation of these two batteries, you see that the negative side is on the same as facing the negative side, and you can't have that. If you're going to put two batteries together, which you often do in small devices, you want them to alternate positive, negative, positive, negative, positive, negative. Okay, so that's how they have to be connected. So even though we have a loop, the batteries are in opposition to one another, so nothing's going to happen. Next one. We have our battery, just one. We have our wires. We have a loop. Okay, actually we have two loops with loads in them. So is this allowed? And the answer is here's one loop, here's another loop. Both are valid, so this is a yes. Okay, in fact, since there are two separate loops from the positive to the negative, this has a special name. This is called parallel circuit. And we'll again talk much more about that because it's a pretty important way to connect multiple loads to one source. So let's compare this with series. In series, there was one path from the positive negative. In a parallel, there are two paths. All right, this one should be pretty clear. We have all the components, but there is a break, and that break means that there is nothing happening. All right, this might be a switch that has been opened, so if we close the switch and complete the circuit, then things will turn on. Okay, last one. This is a subtle one. We have our battery, we have our wires, we have a load. And if you look closely, we have two loops. Okay, so one loop will go like this, and the other loop will go like that. The second loop passes through the load. That's good. The first one does not. And because it does not, we have a short circuit. In other words, there is a path that goes from the positive terminal to the negative terminal without ever passing through a load. And so, nothing is going to go through this one because it doesn't need to. It takes the path of least resistance. All right, so there's our quick introduction to the basics of the circuit. Our next lesson, we will focus on what we measure about that circuit.